We're coming now to the end of our course. We've gone on a journey from unitary dynamics through to the derivation of an effective equation of motion for a system embedded in an environment. So we studied examples, quite a few examples of systems embedded in various environments. And we've studied situations where the generator of time evolutions can be effectively modeled when you just care about the system by another equation of motion. So we've had this situation where we know that the entirety of the system and the environment, they evolve unitarily. And the generator of time evolutions is some Hamiltonian here, and the time evolution itself is some unitary process. But then when we found that when we restrict our attention to just the system, in other words, we trace out the environment, then although the dynamics of this system cannot exactly be described as a linear equation of motion, to a very high degree of approximation, we found equations of motion for the system alone, completely neglecting the environment. So we've been finding equations of motion that look like this. Where now we just have the Hamiltonian for the system, some effective Hamiltonian for the system. And we have, to be completely correct, a plus sign there. Somewhere there's a half. Well, we'll put a 2 here. Yeah, that'll do. Well, I think that's easy to read. We've managed to find an effective equation of motion for the system alone, the state of the system alone. And this is no longer unitary. Right? So this part, this effective Hamiltonian part here does generate a unitary time evolution, but these bits here, these generate non-unitary dynamics, so that an initially pure state, if we call this object here L of rho, which we started doing last week, so that an initially pure state can go to something not pure. And this, of course, is necessary if there's to be an exchange of information between the system and the environment via a unitary process. Now, in all the examples we considered, we saw that the equation of motion, the effective equation of motion we derived looked like this. And when you see something one time, you may think it's just a special case. When you see it 2 times, you start to wonder. And when you see it 3 times, you think there might be a pattern there. And last week, we started the derivation with a formal proof that this kind of equation of motion occurs if and only if you want the dynamics generated here to be completely positive. So that we want to today finish off that discussion and then move on to our final topic for this course, which is quantum trajectories, which is, if in some sense, what the experimentalist sees when you solve this equation of motion. All right, what we did last week is we said this thing here, this super operator, it takes a density operator and provides you with another density operator. We wrote that as ES. And we looked for the most general structure that one of these ES's can should have. So we noted that E of naught does nothing, and we also noted that if we do a bit of ES and we do a bit of ET, then in all the examples we considered that's the same as doing ES plus T. Okay? So these are two properties that we noted about equations of motion like this, and it's natural to wonder, I think, once you see a couple of properties, could it be that just these properties alone are enough to guarantee that the equation of motion that this channel here satisfies is of this form? And the answer is yes. And we started last week the derivation of that result, and today we'll finish that off before moving on to the quantum trajectories or quantum jumps approach. So I'll just continue on from last week and summarize all the results in the form of a theorem. Theorem due to Lindblad. That tells us exactly the structure of a collection of maps ES that satisfy these two properties. And if you remember last week, we saw interesting things like continuity implies differentiability. So if this thing is a continuous function of S, it's also differentiable. And we also saw that it has to be the exponential, any such map here has to be the exponential of a L of a specific form. And now we're going to finally summarize all this information together. All right, this is the statement of the theorem we're going to prove in the next couple of minutes. It turns out we've more or less proved this theorem completely. We're just going to summarize some of the data that we already have at hand. Last week we discussed things called dynamical semigroups. We already derived some structure results about those. If we delete trace preserving and completely positive, if you have a dynamical semigroup, it's always of this form. If you add in the words completely positive, then we discovered last week that this L has additional structure, and I'll write that down here. minus or plus? Minus. This is what we learned last week, that if you impose that this semigroup is linear and completely positive, then already you know that ES is some e to the power of SL, with SL having this particular structure here. So this is not at all generic. We didn't quite prove that, actually. We loosened this up a little bit. So the only data that we have to impose now for this final result is this word here, trace preserving. It's the only extra stuff we have to sort out. And the reason we want trace preserving there is we want probability to be conserved. So trace preserving just means that as time or as S passes, the density operator you get by applying ES to some initial state is still a density operator. It still has trace 1. The probability hasn't vanished into thin air. So we have to just work out how to impose that condition, and then we'll hopefully arrive at this structure for this L super operator. So let's go straight to the proof, which is basically linear algebra. In order for E to the power SL to be trace preserving, you need that the probability is conserved, and that's the same as demanding that the trace of L times rho is 0 for all possible rows. And you can get that by just differentiating the trace of e to the s rho. Trace of e to the s times rho equals 1 implies that trace of L times rho is 0. Just do a derivative. But L, we already know that L has a certain structure. It's not just any L, it's not just any super operator, any matrix. L has this particular form here. So we're going to now find out what does that condition there imply for this operator here. So let's give this equation a number or a star. We input the equation star and we end up with this equation here. Oops. We're going to introduce a new matrix here, which you won't have seen before, phi star of the identity. So what is this matrix? Well, it's a matrix that satisfies the following equation. It just is, it's a matrix that has the property that it's identical, that its trace against rho for all rho is exactly the same as just doing the trace of phi on rho. So we can rewrite this equation here. So parenthetic remark. We've got this equation here. We could move these two terms to the right-hand side, apply the cyclic rule of trace to get the k dagger on the other side, and then we could write that these two parts as this. And this term here, according to this equation here, we write like that. But this has to be true for all rho, which means that this matrix phi star 1 equals this matrix k plus k dagger there. Now I'm going to quote a result from your quantum information course that you are presumably taking right now or have taken, or if you haven't, then you can look this up. Any completely positive map phi, we didn't actually cover this in this course. I don't think we did. It's a structure result about completely positive maps called the Krauss representation. And it says that any CP map can be written in this form for some LJs. So this is it's not particularly difficult to prove this using the information we have looked at in this course. I'll leave it as an exercise for you just to look it up or to just derive it yourself. So this means that if you use this formula here in the definition of phi star 1 here, we'll see that this phi star 1 has a very special form. In fact, you learn that phi star 1 is just this sum of these L subscript j super dagger L subscript j matrices. And that's just a consequence of this equation here and this equation here. But now we're basically done, because if you look at the object we started working on, it's this one here. We know that phi of x has this form. Well, that's that bit there. And we know that k is related to these LJ daggers by this result here. So it's just a matter of somehow pulling out from k a Hamiltonian h and this anti-commutator here. So I hope you can see that all the symbols are written on the board. It's just a matter of just working out how to get from k an h and an anti-commutator like that. And it's not so difficult. This one, thankfully, is it's just a matter of solving a linear equation. So I'll summarize what we now know. We now know that Lj has this form, sorry, L has this form, minus K rho minus rho K dagger. So far, this is what we know. And actually, I'll just tell you the answer. You could sit and work it out yourself, but it turns out this does the job. You can always do this. This is K is some arbitrary matrix. So you can always write an arbitrary matrix as a sum of a Hermitian part plus I times a Hermitian part. It's just like complex numbers. You can always write a complex number as a real part plus I times an imaginary part. And if we just give that the imaginary part the name H, and we give the real part, the Hermitian part, the name that, we just got to check that this is consistent with what we know about these matrices here. I leave that as a little exercise. It's really just solving a simple linear equation. And we're actually there. Already, it's a little bit anticlimactic. There it is. That's actually already the advertised form. So this result, this theorem of Lindblad, confirms something that we hoped was true, namely that when we did this derivation of the master equation, that the resulting effective equation of motion is a physical process by itself. It could have been, after applying Taylor's series and truncating, that the effective equation of motion for the system density operator that we derived was not a completely positive map because we applied approximations. There's no reason for it to have been a completely positive map. And therefore you would have to say, oh well, okay, it's an effective equation of motion, it works for some time beyond which it takes a density operator to something that's not a density operator, then we have to include more terms in the Taylor's series and truncate further along. And that would have been a bit of an dissatisfying situation. But here we've got a result that tells us we can live in a universe of implementable processes in quantum mechanics. So any time you have an equation of motion, an effective equation of motion which has this particular form, the generator, then you know that it's an implementable operation in quantum mechanics. There exists a way to implement it. And that's, I think, a tremendous result. There's no, this didn't have to happen, but it does happen, and it happens often enough. that it's extremely useful thing to know. The only question now, I suppose, is that if we can go the other way. So we've gone from, so far the direction we've been going in this course has always been, we have some big system plus environment. We look at the system, we neglect the environment, we find an effective equation of motion for the system. And now, whenever it has this form, we know that that by itself also generates a legal operation in quantum mechanics. But we can go the other way. Suppose we have a Lindblad equation, we just wrote one down, of this particular form, with some LJs that we like and some H that we like. Could it be that there's a unitary process whose dynamics, whose effective dynamics generates exactly this equation of motion? Could it be? That's the question that we'll focus on in the last part of this course. There's a hint, actually, that the answer might be yes, and that comes from continuous measurement. So if you recall 2 lectures back, we looked at a model for continuous measurement of position, and we saw that there's this it's an energy not conserving process, but it's still a unitary process that you can implement in quantum mechanics. We saw that there is a way to go from a Lindblad equation of a very special form to a unitary operator, a dilation, which implements this effective dynamics. And we're going to take that one step further in the final part of this course and derive a general result. So anytime you have an equation of motion generated by a Lindblad equation, you can implement it with a sequence of unitary operations on a bigger space of a very special form. This falls under the heading of what's called quantum jumps. So quantum jumps, what I'm about to show you may seem like a theorist's plaything, but it's more than this. So theoretically, it's a very interesting way to realize non-unitary dynamics. And secondly, quantum jumps are actually what you see in the lab when you look at detectors. So there's a double purpose to studying this final topic. So far, to summarize so far, we've gone from what we do know is that if you take a continuous measurement process, which is a big unitary, you can get a Lindblad effective equation of motion. Okay, that we know. But can we go the other way? The answer turns out to be yes, and we're going to study that right now. I'll put hats on these things. This is about as general. No. I'm going to drop the J's for this purpose. Yeah. So I'm not going to do the full general result, but once you see the argument, you should be able to see how to generalize the single Lindblad term a case to having multiple LJs. So I'm not going to do the most general result. This is what we're going to do now. We're going to derive this equation of motion as the result of a generalized continuous measurement process. This measurement process is dichotomic. There's two outcomes for this measurement process. You either get 0 or 1 when you apply this measurement apparatus on your system. 0 we interpret as no click or no result, and 1 we interpret as click, like some photon counter clicks. Let's be a little bit more specific about the interpretation of these two operators. So we have this measurement operator here. This is actually an instrument, not a POVM, as we'll see in a second. This operator here is meant to represent the situation where our detector does not click in a time window dt. And this measurement operator here is meant to represent the outcome where the detector clicks in a time dt. So it's indexed by time. Time is built into these measurement operators here. And think of dt as being small, is arbitrarily small yet finite. So it's not quite the dt infinitesimal of calculus at this point. If you think back to our continuous measurement process, it had a form very similar to this. We modeled a process where we measured the system every short unit of time, every dt of time, and the measurement operators that modeled that measurement had a form where they themselves depended on time. And that's the only subtle difference between what we're modeling here and some other process where we just repeatedly measure some measurement operators which don't depend on time. Oops. So you can check that these two measurement operators give a POVM. They add up to the identity. So it's a legal generalized measurement in quantum mechanics. There exists a process which will carry out this operation. And the way to think about this is you have time, you have your system, and you break up time into these time bins, each of width dt. So dt is set by the resolution of your apparatus. I don't know, 10 to the minus 16 seconds. I'm not sure what dt's are, kind of depends on frequencies, resolutions, and so on. And every dt, you apply this dichotomic measurement to the system. You do a measurement on it, check, do you get a click, Do you get a no click? Proceed and then repeat this. Click, no click. And continue to do this throughout time. So the measurement apparatus is always on and always interrogating the system. Now these particular, why would you choose a dichotomic measurement looks like this? Well, because it'll give the answer in our case. You can argue that it should have a form like this with a dt here and a square root dt here. I won't do that. I'll just take the result, and it's an existence result for today. There exists a measurement process whose effective dynamics is given by this. But if you want to actually get into the microscopic model of why this makes sense, then you have to get into more details about detectors, which we sadly don't have time for in this course. Now, if you remember from our discussion of just continuous measurement of position, you have two cases. You've got the non-selective evolution and the selective evolution. The non-selective evolution is where the apparatus does the measurement, but you don't look at the answer. And the selective evolution is where you look at if the detector clicked or not. And it's just a matter of using this instrument here, the definition of it. So the definition of this instrument is that the posterior state after the measurement has taken place will be m0 rho m0 dagger plus m1 rho times m1 dagger. And of course, you have to divide by the probability that you got no click, which is a trace. It's a non-selective evolution. We don't look at the result of the measurement. Now it gets a bit tedious. We have to substitute in what m0 is. M0 is this somewhat unintuitive formula there. Oh, there's one thing I forgot to say. What's this R? R is C dagger C. Now there's no harm in interpreting, for the purpose of this derivation, C as the annihilation operator of a photon or a boson or a fermion. In which case, this R hat is the number operator. It's proportional to the density of bosons or fermions in, say, an output beam. All right, let's substitute in then this formula here, and we'll see we'll get like 8 terms on the top and 8 on the bottom, and then we'll have to start Taylor expanding. So I'm going to cheat and not do the bottom. That's the probability of no click. This is the probability of one click in time dt. Yeah, I know there's something. Yeah, there's something odd here, isn't there? What have I done wrong? This equation here is wrong. So the non-selective evolution, I'll just box the equation, then it's correct. That's the non-selective equation evolution. These two you can regard as the definition of P0 and P1. But they cancel out. So yeah, I just, for the sake of the physical picture, I've thrown in the P0s and the P1s, but they cancel, so I needn't have done that. So I hope that's not too confusing. Another way of making it maybe less confusing is just to do this. Okay, now it should be, I hope, intuitive. We just have this expression here which we can expand to order dt, not dt, not any higher dt's. We could expand to dt squared, but we hope that those terms will vanish. Well, it's more like dt, squared. Now I think you can see the Lindblad equation practically appearing in front of you. Okay, that's it. That's the non-selective evolution. But that's not what we're interested in today. This just confirms that this model of continuous measurement here will give this Lindblad equation as its effective dynamics. The next step is what we're interested in. We want to understand what's the selective evolution. What does it look like? If we look at the measurement record. So a couple of words on why you might even want to look at the selective evolution. Well, one is you actually own a measurement device that can be modeled by these two operators. So you might have a photon counter which records 0 or many clicks or no clicks. And then as the experiment proceeds, as you continuously measure with your photon counter, you get a measurement record. You get a line, and every so often there's a click. And then you want to understand what process did the system undergo to lead to that measurement record. And then you might hope that if you average over all your measurement records that you can understand the process that the system went through. It had better have been that, right? So that's at least one motivation for why you care about the selective evolution. It's because that's what you actually have. That's the data that you collect at the end of the experiment, is a sequence of clicks. And to look at the selective evolution, we're going to have to understand the probabilities of there being a click and there being no click. So the probability of there being a click is the trace of C dagger C times rho times dt. This is crucial, right? So in a little time window dt, the chance that your detector clicks is proportional to dt to the tune of the number of, say, photons in the right mode. So if you halve your measurement window, the probability of you getting a click gets halved, and so on. And I'm going to call that probability infinitesimal, in the sense that it's arbitrarily small yet finite. There's another probability that we care about as well, that's p naught. That's 1 minus p1 dt, and that's almost 1. And if you look at the measurement record, you divide time up in lots of little time bins. The probability of there being a click anywhere in time is proportional to the width. So the probability you get a click right here and a click right here is proportional to the width. So there's a process in probability theory that has exactly these properties. It's called a Poisson process. And although it looks like, there's like a Zeno paradox, right? The chance of there being a click is going down with the time window. So the smaller you make your time window, the less chance there's a click. So it looks like you never get a click if you send dt to 0. But you get more time bins in a finite period of time. So even though you're reducing the probability of there being a click, there's more places for the click to occur. So actually there's a constant number of clicks that will, on average, occur. Just like raindrops. No, I've already done that. Raindrops falling on the ground or other processes that are Poisson. Let's just analyze how does the system change. So if the system underwent a 0-click event, what's the posterior state? And if the system underwent a click event, what's the posterior state? We have to work it out. I had it written down here before I turn this into a non-selective evolution. So P of rho of t plus dt in a no-click event, what does this go to? And on a click event, what does that go to? Well, it turns out that if the system is in a pure state before the measurement, then after the measurement, it's also in a pure state. So we're going to restrict to pure states. So we imagine the system's in a pure state at time t, and then it undergoes this measurement, this dichotomic measurement, and then we're going to look at what's the posterior state, and it turns out it's always pure. Okay. That's how the system state is updated. Your detector does not click. It was in a pure state. It continues to be in a pure state, and that pure state, posterior pure state, is m0 times psi dt. And if you insert the equation we have for m0, then there's a relatively horrible expression for this. That's if you Taylor expand to order dt. So I hope this formula is relatively intuitive. The posterior state, you just Taylor expand this over this. m0 is given by this thing here. You have to do some things with the square root, which is kind of annoying. But there's nothing more than a Taylor series here. That's the no-click event. So to order 1, the no-click, to order 1 in a no-click event, the state after the measurement is the state before, right? That's what that means. But there is some, you have gained information, right? Because the detector did not click, that means that you now know that to order dt there was no photon there, roughly speaking. That information manifests itself in an update of the state here to order dt. So just because you see nothing doesn't mean you haven't gained information. Now we come to psi 1, t plus dt. This is what happens if the detector clicks. Now you know something, right? If the detector clicks, you know for sure that there must have been one or more photons. Let's see. So the state of the system gets updated to a different pure state. Now we call one of these click events a quantum jump. And what we're going to focus on now is describing what a typical trajectory looks like. What does a typical sequence of quantum jumps look like? What does the conditional evolution look like after time t has elapsed? On average, right? Our typical sequence.
Is there a psi missing?
Is there a psi missing? There is definitely a psi missing, thank you. As I said, these quantum jumps are a theoretician's toy, but they are also the best model we have for how conditionally evolved quantum systems behave. So we're going to write now a random variable, n of t. This counts the total number of clicks or jumps that have occurred in a time window 0 to t. You look at your measurement record, you count the number of clicks, add them up. It's an integer, that integer's n of t. If you look at the change of n of t over time, then n of t either is dn of t, like the change in the number of clicks is either 0 or 1, and with an incredibly vanishingly small probability 2. The probability that you see n incrementing by 2 is, in this case, impossible because you've got a dichotomic measurement which can only report 0 or 1 clicks. If you have a better detector that can do 2 clicks or 3 clicks, report 2 photons or 3 photons, you have to redo the analysis. But here, our detector can only say yes or no. So the number of yeses, the number of clicks or jumps in an infinitesimal time, how much can it change by? The answer is 0 or 1, right? So we have this very interesting equation here. So there's only 2 numbers that satisfy x squared equals x, 0 and 1. Now this is a random variable, right? Depending on the history, this dn of t will be a different thing depending on the measurement record. So we can talk about how does it behave on average as time passes. If we average over all our measurement records, repeat the experiment very many times, how does dn behave? How does this expected value of the number of jumps in a small time window behave? Well, it's going to be a number between 0 and 1, right? Because it's either 0 or 1. There's no other possibilities. And if you average over them, then you're going to get something that's between 0 and 1. Of course, we've given that something a name. That's p1 dt. It's just the number of clicks in time dt. And that's proportional to the number of photons, fermions, or whatever you have in the state at that time. And since we're now looking at the selective conditional evolution, we can also write that like this, because it's a pure state at time t. Let's put it all together now and ask what's the change in this pure state, psi naught, as it gets updated after every event. How does it change? This will be itself a random variable, right? d psi of t, the change of this pure state as time passes, is not a deterministic thing. It will be to psi naught with some probability and psi 1 with some other probability. So this is now a random variable. what I'm doing is very sneakily doing stochastic calculus without defining stochastic calculus to you. So we're looking at random outcomes and how they change over time. And to give you a feel for what kind of thing this random variable is, think of Brownian motion. You think of a particle that's wobbling under some unseen forces in a fluid. It's executing this random motion. So you think of this pollen grain in the water, moves around randomly as time passes. And if you'd set up the same initial conditions, it would move around randomly, but follow a different trajectory. Each time you run the experiment, you get a different trajectory of pure states. In the case of the Brownian motion of the particle, the pure state is its position. In the case of this process here, the pure state is the pure state of the system. Okay, that's what d psi means. You take psi after in the next time bin and you subtract psi from it in the current time bin. There is a formula we have for this process that comprises of a deterministic part and a random part, a non-deterministic part. And this is it. There's only one bit of randomness on the right-hand side, and that's this dn. If dn was not a random variable, if dn squared equals dn was always 0, then the selective conditional evolution would be deterministic. The system would always evolve according to this process here. There would be no randomness in how it evolved. Of course, for that to be the case, it would necessarily be that this expectation value here was 0, because the probability that you get a click is proportional to this, and similarly that term there would have to vanish, so you'd actually get unitary evolution. Now there's a way to write this down in a different notation that's used quite a lot in practice. And to do this, we're going to first exploit the fact that dn times dt is of an order smaller than dt. So if dt is a small but finite number, then this is a smaller yet finite number. It's actually of order, yeah, that's right. So in going from this equation to this equation, we've just thrown out this one term here, dnt dt. And now we come to check that we did everything right and we didn't throw anything out in this approximation that would ruin the effective dynamics. So the state of the system up to time t, this is a random variable, right? It depends on the measurement record. This is a random projection. So it depends on the measurement record n of t, which is random. So this projection here is a random variable depending on a random variable nt, and we're entitled to take the expectation over all these measurement records. So what's that doing physically? That's not looking at the measurement record. We're ignoring the measurement record here. It better be the case that that equation, that density operator follows the Lindblad equation of motion. Otherwise, we've done something wrong. Here we see a new wrinkle in all of this. If you study how a projection updates as time passes, well, you work out what psi t plus dt is, and then subtract from it psi t, but as a projection now. Well, you have to include all terms of all orders in t here. And there's this additional term which can occur. This is the difference to what you might be used to with unitary evolution. And if you insert this expansion we have up there for d psi and collect terms to order dt, then we'll get the following equation. And to write that equation down, we're going to introduce these two super operators. This is just notation here. G of C is some super operator. H of this thing is some super operator. And it's a little exercise just to check that when you insert these expansions and you use these definitions here, that you indeed recover the Lindblad equation that we started with. Okay, to do that derivation, you need to just use these two observations here, namely that dn times dt is something smaller than dt. And secondly, that the expectation value of dn, this random variable dn, times by any function of a projection happens to have this form here. You can check that very quickly. All right, so that's how the conditional evolution of the system looks. If you have some measurement record n of t, you find where the clicks are, and where the clicks occur, the system updates to psi 1, and where there's no clicks, the system just continues to evolve according to psi 0. So let's just have a look at a typical solution. So if you look at n of t as a function of time, then what does it look like? Well, it looks like a staircase that grows, right? This is just counts the number of clicks that occurred up to time t. So it's something like that. And these are the click events here, t1, t2, t3. At time 3 there was a click event, time 4, and so on. And you can ask the question, what can we infer about the system evolution? Well, if it started off at a pure state psi 0 at time t, between the clicks, it's just evolving according to this funny operator down here. So, do I have space? Yeah, I guess I do. I can just about do this. Oops. So psi at time t is psi at time 0 evolved. And how does it evolve? Well, between clicks it evolves according to the time-ordered exponential of 0 to t1 minus IH minus this expectation value of c dagger c minus c dagger c on 2 ds. So this is between the clicks. The system evolves. If there was no clicks, it would just be evolving unitarily according to Schrodinger's equation. But because there's no click and you're gaining information, it's evolving non-unitarily according to this funny thing here. At the instant of the click, the system undergoes a quantum jump according to this operator c dagger. And then, that's at this instant here, the detector clicks, then the state gets updated from psi 0 to psi 1, from psi to psi 1. That's what this thing here is. So that's psi of t1. And then it continues to evolve until the next click event according to this propagator here. And then at the next click event, it undergoes the quantum jump at this instant here. And then it continues to evolve according to this time-evolved exponential ... forevermore until you turn the system off. If there was no clicks then these terms here wouldn't be present and the system would just evolve unitarily. And what can you say when when you don't look at the detector? Well, your system is some probabilistic mixture of trajectories like this, typical quantum jump trajectories. These are called quantum jump trajectories right here. Yes, good. Okay, that's about all I want to say on that topic for today. So I thank you very much.